In this episode, we're going to take the idea of watching a network and translate it into the cloud world, where the network is real, but it does not always look like cables and blinking lights. Beginners often picture monitoring as staring at a dashboard that says everything is fine until one day it turns red. But practical monitoring is really about choosing the right signals so you can notice movement before damage is done. Cloud environments create tons of data, yet most of it is not useful for catching an attacker who is moving carefully. So the hard part is deciding what to pay attention to. The goal here is not to memorize vendor features or chase every possible log, but to learn how to think about attacker movement and then choose signals that expose that movement. By the end, you should be able to explain what kinds of network clues matter in cloud environments, why some signals are stronger than others, and how to combine them so you can tell the difference between normal cloud activity and the early steps of compromise. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. The first mindset shift is accepting that network security monitoring in the cloud is less about a single choke point and more about stitching together visibility from multiple layers. In a traditional building, you might monitor traffic mostly at the front door, but cloud traffic can enter and leave through several doors, and some doors are between rooms inside the building. That means you care about what comes in from the internet, what goes out to the internet, and what moves laterally between internal services. Attacker movement is often quiet at first because attackers want to explore without being noticed, so you are looking for patterns that indicate discovery, probing, and gradual expansion of access. You also have to remember that cloud networks are heavily software-defined. So what looks like an internal connection might still traverse shared infrastructure, and what looks like a simple service call might cross boundaries you did not realize existed. Monitoring choices need to match that reality, focusing on signals that show who talked to whom, how often, and under what conditions. It helps to define what you mean by attacker movement, because the word movement can sound like a movie scene when it is really a sequence of small steps. Movement includes scanning for reachable services, testing credentials, calling management interfaces, connecting to unexpected endpoints, and pivoting from one workload to another. It also includes a kind of movement that is not physical at all, where the attacker shifts their control from a compromised machine to a stolen credential, or from a stolen credential to a temporary access token. In cloud environments, attackers may not need to install loud tools. They can often use legitimate service features and normal protocols in unusual ways. That is why the best monitoring signals are often those that reveal relationships, like which workload initiated a connection, which destination received it, and what changed about the pattern over time. If you can see relationships and changes, you can see movement, even when the attacker is trying to look normal. Now we can talk about signals, which in this context means the data you collect that can help you detect movement. A useful signal has two qualities. It is hard for an attacker to avoid, and it is easy for you to connect to a meaningful story. For network monitoring, one of the strongest signals is flow data, which is a record of connections that includes source, destination, ports, protocols, direction, and sometimes byte counts and timing. Think of flows as a call log rather than the full conversation, because you usually learn enough to spot suspicious patterns without reading every word spoken. Flow signals are valuable in the cloud because they can show internal lateral connections that application logs might not highlight, and they can reveal unexpected outbound destinations that identity logs might not capture. Even when traffic is encrypted, flow patterns still expose who connected to whom and how frequently. For detecting movement, that simple map of connectivity is often more powerful than a giant pile of detailed logs that cannot be correlated. Another valuable class of signals comes from the edges and boundaries where traffic crosses an important line. In cloud environments, boundaries include internet gateways, load balancers, application gateways, and service endpoints that represent a transition from outside to inside, or from one trust zone to another. Signals at these boundaries often include connection attempts, error rates, rejected connections, and unusual request patterns that can indicate probing. If a system suddenly receives many connection attempts on unusual ports, or from a new geography, or at an odd time. That can be a hint that someone is testing the doors. Boundary signals are also helpful because they give you context about exposure, like which services are publicly reachable and which are not supposed to be. When attackers move, they tend to test boundaries to find weak links, so boundary monitoring can catch the beginning of a campaign before the attacker becomes deeply embedded. The trick is not to alert on every rejected connection, but to look for patterns that suggest purposeful exploration. A third set of signals comes from the internal network paths that connect workloads and services. In cloud environments, service-to-service traffic can be extremely busy, which makes it easy for an attacker to hide. But that traffic also has expected shapes. For example, an application tier might talk to a database tier on a narrow set of ports, and a web tier might talk to an internal service on a predictable schedule. When attacker movement begins, you may see connections that do not match the normal shape, such as a workload that normally only receives traffic suddenly initiating connections outward. You might also see a workload that normally talks to one database suddenly talking to several, which can indicate discovery or data hunting. Internal flow signals help you detect pivot behavior, where the attacker compromises one workload and then uses it to reach others that were not directly exposed. The key is building a baseline of expected internal relationships, because without that baseline, every internal connection looks equally boring. Outbound traffic deserves special attention because it often tells you what the attacker is trying to achieve after they gain access. Attackers commonly need to communicate with something they control, whether that is a command server, a staging location, or a place to send stolen data. In cloud environments, outbound traffic can also represent legitimate integrations, so you cannot treat all outbound connections as suspicious. Instead, you look for high signal patterns like a workload suddenly contacting a rare destination, a new domain, or an unusual service category. Timing can be a clue too, because attackers often operate in bursts, especially when they are testing access or exfiltrating data. Volume patterns matter because a large increase in outbound bytes, especially to an unfamiliar destination, can suggest data movement. Even small outbound connections can matter if they happen regularly and persistently, because that can indicate a foothold that checks in quietly. DNS is another signal that can reveal movement because it sits at the moment a system decides where to connect. Attackers often use new or unusual domain names, or they may generate many domain lookups as they probe for reachable resources. Even when traffic is encrypted, DNS lookups can reveal intent, like a workload trying to reach a domain that has never been seen in your environment before. DNS patterns can also show when a compromised workload is attempting to discover internal resources, especially in environments where internal naming is used. Beginners sometimes think DNS is just a phone book, but from a detection perspective, it is also a set of footprints that show where someone wanted to go. Monitoring DNS is especially valuable when you pair it with flow data, because DNS gives you names and flows give you connections, and names plus connections create a story. The goal is not to alert on every new domain, but to detect clusters of unusual lookups, high failure rates, or lookups that align with suspicious outbound connections. Service logs and application gateway logs also matter because they can show how traffic behaved, not just where it went. For example, if a gateway shows a sudden increase in rejected requests, odd user agents, or repeated attempts to access sensitive paths, that could indicate probing. If an internal service starts receiving requests that do not fit normal usage patterns, that may show lateral movement using legitimate service interfaces. The important beginner takeaway is that network monitoring is not only about raw network connections. It is about the behavior of the traffic at important points. Attackers often use legitimate protocols like HTTPS to blend in, so you may need behavior signals to differentiate normal usage from misuse. You do not need to inspect full content to get value, because metadata such as request rates, error patterns, and unusual endpoints can be enough to spot trouble. When you combine behavior signals with connectivity signals, you get a more reliable view than either one alone. Cloud environments also add a special kind of signal that traditional networks do not emphasize as much, which is the relationship between network activity and cloud identity. Even though this episode focuses on network monitoring, it is a mistake to ignore the fact that in the cloud, Many actions that affect the network are made through identity-driven control planes. When an attacker moves, they may change security rules, create new access paths, or attach permissions that allow new connections. Those control plane actions are not flows, but they strongly influence what flows become possible. A beginner-friendly way to think about it is that flow signals show what happened, while control plane signals can show why it became possible. If you see a new path open and then immediately see traffic using it, that pairing is high value. The monitoring choice here is to ensure you have signals that capture both the network events and the changes to network-related configuration that enabled them. Choosing signals is also about deciding what you can realistically store, search, and understand without drowning. A common beginner mistake is thinking that more data automatically equals better security, but too much low-value data can actually hide the high-value clues. The better approach is to start with signals that reveal relationships and changes over time, because movement is a change problem. Flow logs, DNS logs, and boundary logs are often strong starters because they are broadly useful across many attack patterns. From there, you add more specific signals that match your environment's critical paths, like the logs for the gateways that protect your most important services. You also prioritize signals that are difficult for an attacker to tamper with, such as centrally collected logs rather than logs stored only on the workload that might be compromised. If you treat monitoring as a curated set of evidence streams rather than a pile of everything, you will be able to investigate faster and with more confidence. Baselining is what turns signals into detection, because without a sense of normal, unusual does not stand out. In cloud environments, normal can be noisy because systems scale up and down, services are deployed frequently, and traffic patterns shift with usage. That does not mean baselining is impossible. It means baselining should focus on stable relationships and expected constraints. For example, even if traffic volume changes, the set of destinations a workload talks to might remain relatively consistent. Even if the number of connections changes, the directionality of traffic might be stable, like a database that should almost never initiate outbound connections. Baselining can also be time-aware, recognizing that some patterns happen during business hours while others happen during maintenance windows. The reason baselines matter for attacker movement is that attackers usually cause relationship changes, such as new connections, new destinations, new internal access paths, or unusual retries and failures as they test assumptions. It is also important to understand false positives in network monitoring, because beginners sometimes assume any alert means an attacker is present. Cloud environments create legitimate reasons for unusual patterns, like new deployments, auto-scaling events, or the introduction of a new integration partner. If your signals are chosen well, you can reduce false positives by focusing on higher confidence indicators, such as a workload contacting a never-before-seen destination immediately after a privilege change, or lateral connections that violate established trust boundaries. Another way to reduce noise is to incorporate context, such as whether the source workload is newly created, whether the destination is part of approved infrastructure, or whether the behavior aligns with a deployment event. Noise reduction does not mean turning off alerts until nothing triggers. It means making sure the alerts that do trigger are worth a human's attention. When your signals are too broad, you end up training people to ignore them, which is a silent failure mode. Choosing the right signals is partly about respecting the reality that humans must investigate. When you step back, you can see that revealing attacker movement requires a balanced set of signals that answer a few simple questions repeatedly. Who initiated the connection? Where did it go? And did that relationship exist before? Did the behavior at the boundary look like normal use or like probing and misuse? Did the outbound patterns suggest command channels or data movement? Did internal flows suggest pivoting into new areas that are not part of the normal architecture? And did anything in the cloud control plane change to enable new connectivity right before the traffic appeared? You do not need to answer every question with perfect precision to be effective. You need enough clarity to decide whether the activity deserves investigation. With good signal choices, you can build a story quickly, and stories are what investigations run on. That is why signal selection is a foundational skill rather than a technical detail. To wrap it up, network security monitoring in the cloud is about choosing a small number of high-value evidence streams that expose relationships, boundaries, and change over time. Flow data helps you map who talked to whom even when content is encrypted. Boundary logs help you notice probing and exposure changes. DNS shows intent and destination discovery. And behavior signals at gateways and services help distinguish normal usage from misuse. Cloud context, especially identity-driven control plane changes, adds another layer that makes network signals more meaningful when paired correctly. Baselining turns all of this into detection by making unusual relationships stand out, and careful selection prevents you from drowning in noise. If you keep the focus on attacker movement as a sequence of pivots and expansions, your monitoring choices will naturally gravitate towards signals that make those pivots visible. With that mental model, you are ready to go deeper into how identity abuse and lateral movement appear in logs and traffic patterns, because you will already be trained to look for the story rather than just the raw data.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.